Hi and Assalamualaikum. Now we continue our lecture with common collector configuration. As you can see in this slide, there are two types of transistor, NPN and PNP, which are apply with the VBB and VEE, and also grounding at the emitter terminal. The difference here is the current flow. For the NPN, the current flow from IC to IE, IB to IE, and for the PNP, current flow from IE to IC and IE to IB. In common collector configuration, the input terminal is between terminal B and C due to ground at C here. So the input value here is IB for current and VBC for voltage. The output terminal is fixed between terminal E and C. So you can see here E and C. So the value is IE for current and VEC for voltage. So remember these four value, then this value will be plot at the graph for the output characteristic. By examining the input of CB, which is a common base and common emitter configuration, notice that they are the same, where the VBE is equal 0.7. As for that, the input for CC configuration remain the same. For the CE, the output voltage is VCE, while the output current is IC. Meanwhile, in common collector, the output voltage is VEC and the output current is IE. As for IC equal to IE and VCE equal to VEC, only the polarity is changed. So it is said that the characteristic of CE and CC configuration are the same. We have finished three types of configuration: common base, common emitter, and common collector configuration. And now we go to the limits of the operation. For the common emitter characteristics, the maximum dissipation level is defined by PC max equal to VCE and multiply with IC. As for that, IC and VCE must be in this range to make sure their product doesn't exceed the maximum power dissipation. So this is the range for the IC. The ICEO is actually the cut-off region, and then the IC must be less than the IC maximum, and for the VCE is greater than the VCE saturation or the value at the saturation region, and the VCE must be less than the VCE maximum. So total of the product of the VCE and IC is less than the PC maximum. For example, if a transistor's collector power dissipation is specified to 300 milliwatt with IC maximum equal to 50 milliampere and VCE maximum equal to 20 volt. So this is the calculation. For IC max value, then we get the VCE is PC over IC maximum, and we calculate from the given values. So we get VCE is actually 6 volt. And for the VCE maximum value, the IC, okay, we get around, the value is 15 milliampere. So we adding 2 more points to complete the curve. Let's say we take IC equal to 30 milliampere. So what we get from the VCE is 10 volt. If the IC is 25 milliampere and we get the VCE is equal to 12 volt. From the 4 points that we get from the calculation in previous slide, we connect all the points obtained and the curve become like this. This is the point 1, point 2, point 3 and point 4. Okay, as you can see here, the range of the IC, this is the IC maximum. Okay, so you get this kind of curve, and then value at this IC maximum is 50. Then we get the total value of the PC maximum here is 300 milliwatt. For the second point, we get this point, and then the total power is same, is 300 milliwatt, and here also 300 milliwatt, and here 300 milliwatt. So you can see this area, this is the active region, and then the blue area is a breakdown region. So the transistor is only works in this white area. Okay. So remember that for this curve, you must remember that we have IC maximum, and then we have the VCE saturation around the zero voltage, and then the cut-off region here, and also VCE maximum. The same goes for a common base configuration. Its maximum power is defined as PC max equal to VCB multiplied with IC. Okay, remember that for the common base and common emitter, the difference is at V, at the voltage. For the common base, we use VCB. For the common emitter previously, we use VCE. And the IC and VCE range is defined as like this. Okay, IC must be less than IC max, VCB must be less than VCB max, and total power must be less than the PC max value. Now we take a look at the transistor datasheet, which is really important, okay, in your study, okay, because normally the symbol or the name of the value has a little bit different from what we learn or we mention in the entire topic. So please take note. If you have transistor datasheet, the transistor datasheet normally is split into 3 sections, where the first one we have the maximum rating. Okay, for the maximum rating, actually these are a value for the limits operation, where you know the PD is actually the PC maximum. Okay, PD you can get here. PD is actually PC maximum. Okay, this is a total device dissipation. Okay, so the value for this one is 625 milliwatt. And for the VCEO here, VCEO is actually VCE maximum. Okay, VCE maximum. And IC, okay, this is the IC maximum. So if you see this table, maximum rating, you must imagine the limits operation curve. Okay, so I list here the relation between the three values. PD equal to VCE maximum multiplied with IC maximum. So you can find its value from this table. VCE maximum, IC maximum, and PC maximum. Second section of the transistor is the off characteristic, where the important one is the ICBO. This is the cut-off current for the common base, and ICO is the cut-off current for the common emitter. And we find another one is on characteristic here. Okay. And on characteristic table, the important here is DC current gain, or actually we call it beta for DC, HFE. Okay. You cannot find beta value in this table because it used HFE as beta for DC. And this is the VCE saturation, collector emitter saturation voltage. And in small signal characteristic, this is actually for the small signal analysis or AC analysis. So the value of beta is different, where we call it beta for AC, and it use symbol of HFE. Okay, so I list down here. Beta DC is actually HFE that we normally use in DC analysis, and this is the HFE that we use in AC analysis.